So now this is our module 2. Our module 2 is all about conservation of energy. Now our first topic for the conservation of energy is its gravitational potential energy or its potential energy. So the gravitational potential energy of a body is in its energy due to its position or elevation. Now there are some problems that will state that for a certain mass, for a certain object, it has a mass. And therefore, if you are looking for a potential energy, even if there is no gravity, but it is in standard condition, is it always equal to 9.81? So the mass given times its 9.81 is its potential energy. Now, this is K, proportionality constant K, which means that just like what we discussed on the last part of our module, proportionality constant K is very important for us to determine the analysis of units. And this Z represents its height, its mass, its gravity, and its height over its proportionality constant K is your potential energy. Now, when you see the change in potential energy is equal to delta P is equal to P2 minus P1, your final potential energy minus your initial potential energy, or your final height minus your initial height. Now, it's when kinetic energy. Kinetic energy is the energy or stored capacity for performing work processes by a moving body by virtue of its momentum is called kinetic energy. When velocity is required, when there is a velocity in the given, you have to determine what is its kinetic energy. Kinetic energy is equal to mass times its velocity or its speed squared over 2K, proportionality constant K, which means your delta K is equal to K2 minus K1 or equal to M over 2K times, sorry, V squared, V2 squared minus V1 squared, or your initial your final speed minus your initial speed. Delta K is change in kinetic energy. Next, internal energy or DU. Internal energy is energy stored within a body or substance by virtue of the activity and configuration of its molecules and of the vibration of the atoms within the molecules. When we say specific internal energy or change in internal energy, it simply denotes U2 minus U1. Now, in the problem, it will also be given, and there is no formula to find the internal energy. It will only be given in the problem. Next, work. Work is the product of the displacement of the body and the components of the force in the direction of the displacement. Work is the energy in transition. That is, it exists only when a force is moving through a distance. Now, work of a non-flow system. The work done as the piston moves from E to F is this kind of equation, which is the area under the curve E of PV plane. Therefore, the total work done as the piston moves from 1 to 2 is, this is your equation. Your work is equal to the integral of P dV. Now, which is the area under the curve 1EF2? 1EF2. This curve, this is your area. This the area under the curve. We say area under the curve, this is it. Area under the curve. Now note, the area under the curve of the process on the PV plane represents the work done during a non-flow reversible process. Now, please take note of this. When we say work done by the system is positive, it is outflow of energy. when the work done on the system is negative inflow of the energy. Now, work done is negative. Work done by is positive. Please do not interchange that because it is different in meaning. Now, flow work. Flow work or flow energy is work done in pushing a fluid across a boundary, usually into or out of a system. The formula for workflow, delta workflow is equal to workflow 2 or final minus workflow initial, or simply PV, your pressure in final, volume final minus pressure initial, volume initial, your PV. Next, your heat. Heat is energy in transit from one body or system to another solely because of a temperature difference between the bodies or system. Q is positive when heat is added. Please take note of this. Q is positive when the heat is added to the system or system. Q is negative when the heat is rejected by the body or system. When the heat is rejected, negative. When the heat is added, positive. Work done by the system is positive. Work done on the system is negative. Am I correct? Let's see. Work done on by the system, yes, correct, is negative, and work done by the system is positive. Please do not interchange these four. Now, the classification of systems. A closed system is one in which mass does not cross its boundaries, or an open system is one in which mass crosses its boundaries. Now, there are certain problems that will state that it is a closed system or it is an open system. Now, conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed. The first law of thermodynamics states that the one form of energy may be converted into another. Conservation of energy is like a conservation of mass, as we discussed on the module 1, part 3, which is the mass entering equals the mass leaving. Here, in the conservation of energy, energy entering also is equal to energy leaving. There is a conservation of energy. Now, the steady flow energy equation. Characteristics of steady flow system. There is neither accumulation nor distribution of mass within the system. There is neither accumulation nor diminution of energy within the system. The state of the working substance at any point in the system remains the same, remains constant. Now, I'm sorry. Now, let's go to this diagram, energy diagram of steady flow system. Now, by applying law of conservation of energy, your your energy entering is equal to your energy leaving. That means whatever energy, potential energy, kinetic energy, internal energy, work that will be entered on the system should be leaving also. Your peak, your potential energy, your kinetic energy, your work, and your internal energy. Now, your heat added also is equal to your heat rejected. So therefore, there is a conservation of energy within the system. So entering denotes its P sub 1, K sub 1, V sub 1, U sub 1, and your leaving denotes your P sub 2, K sub 2, U sub 2, W sub 2. Which is your final and your initial. Your final is your is your leaving, and your final and your initial is your entering. Okay? By summing it up on the diagram, the energy entering the system is equal to energy leaving the system. So, sorry. So P1 plus K1 plus work flow 1 plus internal energy 1 plus heat equals P2 plus kinetic energy 2 plus work flow 2 plus internal energy 2 plus work, or Q is equal to, when solving for the heat, the delta P plus delta K plus delta workflow plus delta U plus W, which is your equation. This is the derived equation for your steady flow energy. Now, the enthalpy of the H. Enthalpy is a composite property applicable to all fluids and is defined by H equals U plus PV, where U is your internal energy plus your pressure and your, what is your V? Your volume. And H equals MH, U plus PV. Now, the steady flow energy equation becomes, when there's an involvement of enthalpy, your P1 plus K1 plus H1 plus Q is equals to P2 plus K2 plus H2 plus W. Excuse me. It is also delta H, your final minus your initial enthalpy. So it is also Q equals delta P plus delta K plus delta H plus W. Now, for better understanding of the equation of the problem, we should answer the first problem exercise. Now, problem exercise. During a steady flow process, the pressure of the fluid substance drops from 200 to 20 psi, which means when you say drops from 200, which means your P1 is 200 and your P2 is 20 psi. The speed increases from 200 to 1000 fps, which means your velocity 1 is 200 plus velocity 2 is 100 fps. Now, take note, I'm so sorry for this. Enthalpy is your pressure and your velocity. This is pressure and volume. No, this is volume. It is correct. Pressure and volume. Okay, let's go back here. Where are we now? Yes, the speed increases from 200 to 1000 fps, your V1 and your V2. Then the internal energy of the open system decreases 25 BTU per pound. So when you say the internal energy of the open system decreases, it decreases to 25 BTU. This is also a change in internal energy. And the specific volume increases from 1 to 8 cubic feet per pound, your V1 and your V2. No heat is transferred. That means Q is equal to 0. Sketch an energy diagram. Determine the work per pound. Is it done on or by the substance? Determine the work in HP for 10 pounds per minute. So you have given a mass, and your HP is 42.4 BTU per minute, which shows the computation. Now, first question, sketch an energy diagram. Now, when sketching an energy diagram, you have to very particular, or you have to very mindful with the diagram. So let's sketch the diagram first. Let's say, for example, we have a certain box. This box is called our system. This is our system. I'm sorry for my handwriting. I'm using only mouse for my tool as my handwritten tool. And it's very difficult for me to write. Next, when drawing a sketch diagram now, just like we discussed earlier, the energy diagram flow, that's it. We have to have this, we have pressure, no, we have kinetic energy, K1. What else? We have work flow 1. And then we have also internal energy 1. Now, energy entering is equal to energy leaving. So therefore, if you have K1 there, you have K2 here. You have workflow 2 here. And you have your internal energy 2 here. Next, no heat is transferred. So therefore, we can not, we can, sorry, we can, we cannot include Q on this diagram, but we need to include your work. Now, since the second question is determine the work, is it done or by the done on or by the substance? You have to guess it first. You have to assume that it's neither done on or done by. So you have two arrows to show the representation of the work. Now, what is our equation? Our general equation for this is based on the schematic diagram we build. Your K1 plus your W F1 plus your U1 equals your K2 plus your W and F2, sorry, WF plus your U2. Plus your W. Okay, since it is your work. Now, for us to be able to get these parameters, we have to solve each of these by using all givens in the problem. Let's go to kinetic energy first. Your kinetic energy is equal to your K1. Your K1 is equal to velocity squared over 2K. Now, your K1 is your 200 feet per second squared. Sorry. This yan, velocity. Velocity is your 200 feet per second. FPS siya ay squared over 2 times your proportionality constant K or your gravity 32.174. Now again, we will be using 32.24 for the uniformity of our solution. But here I will going to use 32.174. Your K denotes your gravity. Here. Okay. Let's change this to avoid confusion. Will be G. Yeah. 32.174. No. It's K because of the analysis. When we use gravity, the unit analysis will be wrong. So let's use K 74 pound mass feet per pound force second square times your 778 feet, sorry, feet, cubic feet per pound, BTU, sorry, this is 77, this is conversion factor, 778 feet, pound force per BTU. To have IBTU per pound unit. Therefore, simplifying it up, 232.2174 times 2 times 778. We have 0.7989973542. That is your BTU per pound mass. So you have your K2. This K2, you have to store it on your calculator. Then let's solve for K2. This is your K1, sorry. You have to save it on your calculator and we solve for K2. Okay. We only change this in this given. K2 equals V squared over 2K, which is your velocity is 1,000. Then 2 times that K, your proportionality constant K, 32.174. Then your conversion factor into BTU. K2 is 2 times 32.174 times 77 is 18.32. Is 19.97493386 BTU BTU per pound mass. Why? Cancel this. You have no, we don't need to cancel this. Cancel feet. We cancel second squared. We canceled pound force. Okay. Then since it is squared, feet squared, second squared. So we have fit also this on here. So we canceled also this. All we have left is BTU per pound mass. Okay, so therefore your kinetic energy 2 is 19. You have to store it also. Then next, your workflow 1. I will go into erase this first. Now your workflow 1 is equal workflow equals to P1 V1. Okay? Equal to your pressure 1, 200 PSI, pound per square inch, multiplied by the conversion factor 144 inch squared, feet squared. Then your specific volume, 1 cubic feet per pound. All over 778 to change as the conversion factor into BTU per pound mass. Okay, we have to cancel pound, your inches squared to inches squared, your feet squared to feet squared. All we have left is, this is BTU. Sorry, we have a wrong. This is feet. Sorry, feet pound force per BTU. Okay. So that's it. All we have left is, since this is a feet cube, we cancel also this feet. No, all we have left is BTU per pound mass. Pound mass, okay. This one, pound mass, okay. Your 200 times 144 times 1 over 778. 37.0179948 BTU per pound mass. So that is your workflow 1. Okay, you have to store also for later use. We will erase, I'm sorry. I'm going to erase this only and this only. So P1, P2, V2, workflow 2. Now this is a pressure 2, which is 20 pound PSI, 144 and your 8, not 1. 8 cubic feet per pound. And the answer is 144 times 8 is equal to 29.61, 43, 95, 8, 9 BTU per pound mass. So this is your workflow 2. You have also to store it on your calculator for later use. Now we already have K1, K2, workflow 1, workflow 2. And we also have your internal energy of a change in internal energy, which is 25. We can now, therefore, substitute all given values. Our equation is K1 plus workflow 1 plus, equals K1 plus workflow 1 equals K2 plus workflow 2 plus delta U, since it is a change in enthalpy, so therefore delta U is on the leaving, and plus your work, which will be the required. Now, your K1 upon storing, is equal to 0.8 BTU per pound mass, plus your workflow 2, 37 0.02 BTU per, I will not write the unit, equals K2 based on our stored value. K2 is 19.97 plus your workflow 2 based on our stored value. It is 29.61 plus your change in internal energy, which is 25. Now, it states that it is decreases, therefore your internal energy becomes negative plus work. Since the work decreases, states in the problem, all you have to do is to make your sign on your internal energy be negative. Then upon adding it up, upon solving it up, we yield to 13.24 BTU per pound mass. Now, there is another question. Is it done on or by the substance? Again, when we say that work done by, it is positive, and work done on, it is negative. So since our work here is positive 13.24, therefore it is work done by. But if the answer here will be negative, we will say it is work done on. Sometimes the work will be negative if and only if there are certain numbers here, or there are certain parameters here that are negative. Like for this example, if this internal energy becomes 250, we therefore conclude that the workflow here may become negative. And if they become negative, it is not wrong. Don't panic, it is that it is wrong. It is correct since it depicts that your work is done on the system. Next, determine the work in HP for 10 pound per minute. So you have BTU per pound mass. I will erase this first because we have nowhere to write. So the last question, determine the work in HP for 10 pound per minute. So we have work which is 13.24 BTU per pound mass, which is work done by the system. So the last question is determine the work in HP. So your work 13 in a 10 pound per minute. So by using unit analyzation, you can get 13.24 per BTU per pound mass multiplied by 10 pound mass for you to cancel out the pound here. And then, since it is on BTU, we have to change it in HP. The conversion factor, as it is given on the problem here, 1 HP is equal to 1 BTU. 8 is equal to 42.4 BTU per minute. So, don't forget to memorize this conversion factor for you to make sure that if it is not stated in the problem, it is not given in the problem, you can solve it. So by dividing, so by simplifying it up, your work in HP will become 3.12 HP. And that is your final answer for the last question. Okay, that's it. That's it for the part 2. For the module 2 of my thermodynamics 1. Thank you.